So for Noctua at Computex, we have a lot of stuff to talk about, all technical, as we've done the last couple of years. We actually have a whole separate video on this thing, but I'll show it briefly. This is a carbon nanotube thermal pad, basically. Super cool. We're not going to talk about it in this specific video, but we do have a full in-depth interview talking about that. Noctua is working with another company, Carbice, to sell pads. They also have this low-profile AM5 cooler, where you can see they're really maximizing the keep out zone on the motherboard. So right up against kind of the limits of the keep out zone for AM5 near the heat sinks, and then just kind of using that memory area, so you need lower profile memory to accommodate it. But that's a 70 millimeter tall cooler. It's not ready to launch yet. They don't have a price target yet, but I just wanted to show it. For the stuff we're actually going to be focusing on today, so the Thermosiphon is back. We've talked about this at least once, maybe twice now for booth visits. And Jakob, off to the side over here, is going to be joining again for now I'm not sure how many years running, but we'll be going over all the details for this, the changes they've done in the last year on the technical side. And then also on the opposite side of the booth, the liquid cooler, which is now actually coming to market. A lot of cool technical detail on that too. So this one is going to be mostly focused on I know this is scary, but education and talking about science. So it should be pretty fun. We brought you this video with our brand new wireframe V2 mouse mat on store.gamersnexus.net, also accompanied by our new Micro Slop t-shirt that's on its way to our warehouse right now. These feature a parody Micro Slop logo with a blue screen of death frowny face, warning marks from a vent viewer, and our rendition of Tux the Penguin hidden away, and of course, Micro Slop. So everyone you pass either thinks you work there for now, or they know your thoughts on AI. The wireframe V2 mouse mat on the GN store was made by Andrew on the team in Blender, fully 3D modeled, and then represented in a high-quality mouse mat that you see here. The mat can easily accommodate a keyboard and mouse, has fine detail with the city built of wireframe components for the heatsink, RAM, because let's be honest, it's the only place any of us can get any now, and cooling tubes, and we use a matching blue stitching for anti-fray with a blue rubber underside for some unique GN flair. We modeled these to ridiculous levels of depth in that there are things in the model that you can't even see in the product because we went that deep with it. Like, for example, the springs underneath the switch, underneath the keycap, that's represented in the matte surface. Head to store.gamersnexus.net to support our deep dive, independent research content like this directly. Okay, so I'm joined by Jakob again. Jakob, we've done this at least a couple years in a row now. Yeah. And last year you had a pretty early version of the Thermosiphon. Actually, this, if I remember correctly, this was like, it looked like that, right? It was just metal and a sheet in the front, a glass sheet. So in the past year, what's the biggest thing that's changed for the Thermosiphon?
Well, I would say the most important thing to mention is that we've made a major leap towards reaching the performance targets we set out. If you recall, last year we mentioned that our performance target is to reach roughly the same performance level as today's best all-in-one water coolers. And we're very happy and excited to show you a prototype here this year that's actually like reaching that target. Last year we were demoing on a 9800 X3D. I stressed that it was not a performance demo, it was a functional demo to show you that we are okay to run like typical workloads, but this is like around 100 watts territory. Yeah. This year we are running a 9950 X3D at 230 watt. Pitting our latest prototype against our AIO. And
looks like a OCCT here running the test.
Absolutely. Okay. Stress test. This is all fluctuating here a little bit. It's not a lab environment, but you can see that at the moment the Thermosiphon prototype is at 81 degrees Celsius. The all-in-one is at 81.5. The point to demonstrate is not that this is slightly better than the other, but just they are roughly on the same level.
Trying to get at least performance parity for thermals, I guess. We've kind of gone over some of the basics of like what you guys are trying to do for the last year, but one of the things I remembered was you had a wall of like 6 different cold plates or something.
Yeah.
Did you end up deciding on what direction to go with those?
Yeah, I think we are pretty set on a specific direction now. Last year, a lot of the stuff we've done, we've experimented with, was about dealing with the high heat flux densities of modern CPUs and the issue these hotspots create for two-phase coolers. If you remember last year, we discussed the thermodynamics background of the boiling curve and that point of critical heat flux where vaporization becomes so intense that bubbles not only rise and form full streams and jets, columns of vapor, but actually vapor cushions form against the surface and thermally insulate the surface against the working fluid, which then causes excessive temperature exactly at those points where you need cooling the most.
You still have a version of that chart here today? Is
Yes,
that over
absolutely.
here? Yeah.
We've shrinked it down a little bit so that we can fit in all the other stuff, but we still have that boiling curve here that starts with the phase of nucleate boiling, isolated bubbles, then from the inflection point on goes into jets and columns, and here's the point of critical heat flux from where the amount of heat that we can transfer per excess temperature, so temperature above the separation temperature of the working fluid, drops drastically until the Leidenfrost point where the film boiling phase starts and the hot surface is fully insulated with a vapor film. So that's still the background we're battling with, but we've taken a slightly different approach in the end. A lot of the cold plates we've shown last year were focused on like mitigating that hotspot formation on a structural level, paradoxically making the inside surface of the evaporator a little bit cooler where the hotspot is so that we don't run into these kind of phenomena. And what we ended up doing now is that we actually have vertical guiding ridges that have the main purpose of making the fluid circulation inside the evaporator more controlled, more predictable, and with having better circulation inside, we are becoming less dependent on that specific hotspot optimization because we have more fluid going over the surface, removing heat.
Is there, I'm sure there's a purpose for it, the height difference here between...
Yeah.
So walk me through that.
Definitely. So when we look at it at a micro level, the first thing that's important to point out is that when vapor rises, it also drags liquid fluid up with the vapor. And what we want to have is a as smooth as possible recirculation of that liquid down in the evaporator and up again. And the different height ridges allow for pathways for the liquid to circulate back down without being disrupted by turbulence from the upstream vapor and liquid. With the circulation being more predictable and more controlled, we have less issues of vapor basically shooting out that so violently towards the top that it drags up drops of liquid fluid into the vapor line.
Basically, traffic jam is what I came to when you were describing it. But you're just talking about, I guess, is this liquid here? Bubbles of liquid?
Yeah,
okay.
liquid droplets, basically clogging the vapor line, restricting its efficient diameter, and thereby increasing the fluid resistance for the vapor to rise. And any kind of this undesired flow impedance in parts of the system can cause the performance to go down. And this is why it's so important to make both the evaporator, circulation in the evaporator, but also the condenser work more predictably. Because whenever we have situations like, for example, in the condenser of, in this case, premature condensing, where in one or more of the microchannels of the condenser, the fluid condenses before it actually should, that increases flow resistance through the condenser, and then may end up with liquid fluid pooling in the condenser and less fluid being available in the evaporator, which can lead to dry out conditions in the worst case.
With an AIO, typically they'll leave a little bit of air in the liquid cooler for a number of reasons, shipping being one of them. But with a thermosiphon, do you follow the same principles? Do you leave any air in it at all?
No, we absolutely don't want any air inside our system. The system, we create a vacuum in the system before filling in the refrigerant, and that's crucial because any non-condensable gases would accumulate in the condenser and then actually reduce the performance of the condenser, insulate it towards the fins where the fans can then remove the air. Over the years, permeation will introduce minute amounts of air, but this is precisely why we are so careful and deliberate in selecting the tubing materials to make sure that we reach a 10-year lifespan without any significant impact of performance due to permeation. When you look at a water cooling radiator, you just care about the delta T between inlet and outlet. How that happens, where that happens, you don't care. With the condenser, if you have premature condensation in one of the microchannels and then increased fluid resistance in that channel, that's a major problem. Or conversely, if you cool down the working fluid too much, you end up with a phenomenon called subcooling, where the returning liquid is too cold and takes longer to vaporize. And basically that means that the system is working in a single phase stage until the liquid reaches the desired boiling point, and the entire system is not optimized for single phase.
Right.
So you really need to adjust fill rate, pressure and temperature gradients within all parts of the system, make sure that the fluid balance is ideal in all parts of the system to ensure consistent performance.
So what's going on here? I see non-treated surface with micro layer. This is giving me some hints. And then micro layer of porous sintered copper also sounds like some concepts taken from other parts of cooling. But what is it special you guys are showing here?
Micro layer of sintered copper is very critical to ensuring the performance levels we're seeing now and to increase hotspot resistance as well. So it's pretty similar technically as what you use in a sintered copper heat pipe. So small copper particles that form a porous mesh, and the benefit of this structure is quite similar to what you have in a heat pipe, that you have very strong capillary action, but at the same time the porous structure allows for enough pathways for vapor to escape. So we're not running into these conflicts here, and also the vapor pressure is generally high enough to break through layers of liquid fluid. Compared to a heat pipe, the technical situation is different in the sense that we're in a pool boiling environment, meaning that in a heat pipe you have liquid flow only through the wick, and the open area in the middle is vapor. In our case, we're in a pool where vapor has to find its path outwards of the wetted surface. Due to the high surface area of the copper wick structure, we have better heat transfer, better nucleation, and this is not a puzzle piece to avoid the vapor blankets forming.
I guess a vapor blanket really just does it create an insulating layer?
Yeah, totally. For any typical working fluid, the gaseous phase of the fluid is higher thermal resistance than the liquid phase, and that means that if you have a vapor blanket forming somewhere, it will insulate from a thermal perspective, and that's why it's so critical to avoid this.
Right. You want to use the phase change for its benefit, I guess, and then kind of get it out of the way as quick as possible.
Yeah, absolutely. If we look at it at a bit more micro level, it's actually the so-called evaporating meniscus that does the heavy lifting. That's the extremely thin, minuscule vapor to liquid interfaces that form within all these crevices of the mesh structure. And zooming in deeper once more, the way the meniscus works is that we have an absorbed film region where the liquid film is extremely thin, so adhesion forces are very high and thermal interface resistance is very high, so not much evaporation going on at all. And then we have the thicker bulk region where the liquid film is so thick that the thermal resistance is also quite high. But the intermediate transition region is where the magic really happens, because the thermal resistance is low, and when the fluid evaporates, it will cool off the thin liquid layer, and then that increases surface tension, and you're getting these Marangoni stresses or Marangoni flows that pull additional liquid downwards to vaporize again. And the vaporizing liquid is drawing in additional capillary actions, and that's the beauty of the vaporization enhancing surface. This cold plate here is actually with the surface enhancement applied with the porous copper layer. You may wonder why it looks grayish. That's due to the additives that we use to control pore size. Tuning the pore size, the particle size, and the layer thickness of the entire thing is crucial to really getting the best out of it.
Right. Let's hop over to the AIO and wrap there. Yeah. Okay. So on the AIO, we just got these into the office. You'd sent them, so we'll be testing those soon and posting benchmarks on the channel. So we'll have all those numbers pretty soon. But you guys do have some interesting stuff to talk about here too. One of my favorite tests, I still haven't been able to use a vibrometer for any kind of testing yet, but I've seen them in a lot of labs. And this, correct me if I'm wrong, I think when we've seen these, it's been for like video cards and power supplies where they'll shoot lasers at it to basically look for really, I'll say, microscopic movement in the surface, right, for noise.
Definitely. It's a contactless surface vibration measurement device. And the reason why we care so much about surface level vibration is because the vibration will typically translate into airborne noise. And obviously, we want to cut down on that as much as we possibly can.
Just looking at the frequency spectrum and spread, I'm seeing it looks like maybe some improvement in some of this like 2K or 2500, but the chart up there, it really looks like most of the improvement's going to be in that, we'll say like 4,000 plus hertz range.
Yeah, I would say we definitely have some improvements in the lower frequency areas as well. You can see those spikes around like, what is this, maybe 330, 500, 670. They are slightly reduced, but the bulk of the improvement is definitely in this like 1500 to 2000 hertz zone, and then the 3 kilohertz to 10 kilohertz zone. So we're really significantly reducing the high frequency noise content. That's also something that's clearly audible in the video. We can share that. Maybe you can cut that in. It will also be available on YouTube from our side. So the important message that we want to get across is that sound pressure level reduction in terms of like dBA is one important thing. We're seeing typically 1 to 4 dBA low noise levels with the noise damping cover installed. But the sound quality improvement is another very important aspect that may often be easier to perceive for customers than the actual SPL drop. Last year we were still looking at the 3D printed dummy. Now we have the final foam here, 2 layers of open pore soft acoustic form and a dense barrier in between to target the lower frequencies. The whole pump noise absorber is mounted on these floating silicon mounts that ensure that no vibrations, or as little as possible, as few vibrations as possible, are transmitted to the outer shell of the cover. And as we've discussed last year, the entire assembly works both as an acoustic soundproofing device, but also as a tuned mass damper that reduces vibrations.
Right. What are we looking at for these like sort of distribution maps? What is that showing?
So you can see our damping cover at the bottom here, and 2 covers with screens above. And what we can see from the measurements is that the covers with screens have a much higher vibration amplitude and a much bigger gradient in terms of high to low. Versus our cover having a lower amplitude in general and a much smoother gradient, so we can spread the entire vibratory energy over a smaller surface area, and this will transmit into airborne noise much less than these high differences in terms of vibration amplitude. So the way psychoacoustics work and the way these types of analysis work is that we use standardized mathematical models that have been developed in the scientific literature, and then score recordings based on that on these models. And so in this sense, it is very controlled, very reproducible, and not something subjective in the sense of you and me listening to the video and you say, it sounds better, I say it sounds worse. This is like as controlled as it gets for something that is intended to reflect subjective perception.
Objective basis for noise, yeah. I mean, for example, like typically higher frequency people find more annoying, so there's some objective truth to that.
Totally. We discussed about the frequency spectrum and how we can very efficiently reduce high frequency content, and that is, for example, reflected in the sharpness score. Sharpness is a metric that describes how much high frequency content you have in the acoustic spectrum, and you can see that we're doing much better with the cover. Loudness is another key metric. Where that describes perceived intensity of the sound, but it's not directly translatable into dB or even dBA that can be converted into like physical Pascal pressure differences, because it factors in things like sensitivity to critical bands, temporal composition of the sound signal. And those are all the complexities of acoustics that get lost in a simple dBA score. Yeah. You mentioned annoyance before. It's maybe not as commonly known as, I don't know, loudness, sharpness, tonality, roughness. This is something a lot of people know. Annoyance is a composite score that basically combines all the other key scores. So from our perspective, it's maybe the most important one, because it shows that the overall net result is very positive with our cover.
What's the unit of measurement here?
This is just for psychoacoustic annoyance. It's a dimensionless abstract unit, so it cannot be converted into anything because it's based on subjective perception.
Cool.
One thing I just realized is that we should mention the differences, I think, regarding last year's data, regarding the SPL measurements, because some viewers may remember that last year we had an average improvement of, I think it was 5.7 dBA. Now we're talking about 1.4. Why is that? Did the cover get worse?
Was this because you were testing free-floating rubber band suspension versus...
Yeah, exactly. So last year's data was in a lab, pump suspended on rubber bands. So we have no way for the vibration or acoustic energy to go except into the cover. And this data now here has been collected on a real user setup, AM5, installed inside the Antec Flux Pro Noctua Edition case. And in such a scenario, obviously we have limited control over how vibration and resonance spread through the CPU, through the motherboard and into the case. That's the first reason why we're seeing slightly lower scores now. The second reason is that we changed the measurement methodology. Last year's data was from a standard fixed distance between the microphone and the noise radiating surface methodology, and now we've switched to keeping the distance between the original source of noise and the microphone constant. So that actually means that the microphone is closer to the noise radiating surface with the cover installed, just to make sure that we cannot be accused of using a test condition that would favor our own product.
So they do have other stuff too. We already filmed the Thermal Grizzly Wire View collaboration. That's on the channel if anyone's curious. But that'll wrap us for the Thermosiphon and for the cooler, the AIO. There's also the pad video coming out separately. Jakob, thank you again.
My pleasure. Thanks for coming.
Absolutely. And we will see you all next time.